So first off, let me tell you, when you look at the tangent graph, it does not have a period of 2 pi. The period for tangent is pi over b, not 2 pi over b, because the normal period for tangent is just pi. So this is the period formula for tan and cotangent. If ever you're asked to find the period of tangent or cotangent, do not use the formula 2 pi over b, use the formula pi over b. So what do we have here? So you can see that if I draw some vertical asymptotes in here, there's a vertical asymptote here at negative pi over 2. We'll talk about why that is. And there's another vertical asymptote at pi over 2. So hopefully you remember what creates vertical asymptotes from your college algebra experience. I might remind you that real quick in a second. So the idea is, if you notice, the tangent function basically looks a lot like y equals x cubed in college algebra. The difference is y equals x cubed does not have vertical asymptotes. This graph is trapped forever between negative pi over 2 and pi over 2. It goes up forever and down forever, but it never crosses these vertical lines. So if you just looked at that, we have a half of a pi to the left of 0, right? This is negative pi over 2. You have a half of a pi here. And then to the right of 0, from 0 to pi over 2, you have another half of a pi. So if you take a half a pi and add another half a pi, you get yourself a whole pi. So it takes pi units. The horizontal distance between these vertical asymptotes, pi unit. So that means the normal period for tangent is just pi, which can be thought of kind of obvious, because if I write tan x, that means that the number in front of the x is a 1. That means b is 1. And if you replace b with 1 in my formula over here, the correct formula, you'd get pi divided by 1, which is just pi. So when b is 1, your normal period for tangent is just pi divided by 1, or pi. The period equals 2 pi over b. That is the one you use for sine, cosine, secant, and cosecant. But we're not talking about those right now. We're talking about tangent, cotangent. So that's not supposed to be tricky. That's just the way things are. So what else can I say about tangent? Real quick, I want to just illustrate at least why some of these points make sense to me. So if you remember in your college algebra experience, let me go to Desmos and just do you a quick reminder of what creates vertical asymptotes back in college algebra. So you might have something like, say, x plus 2, that quantity, x plus 2. This has nothing to do with trig. This is college algebra, but the idea is the same. And maybe I just do x minus 4 or something. So what you had was, you had an equation that was a fraction, and you had to look at where the numerator of the fraction was going to be 0 and where the denominator was going to be 0. And for the sake of time, I'm just going to do this mentally. If the top is 0, that would happen at negative 2. What happens when you have a fraction where you have 0 on top? Well, in math, 0 divided by anything is 0. So if I plug in x equals negative 2 here, the fact that it makes the numerator of the fraction 0 means that the whole fraction will be 0, because 0 divided by anything is 0. So whatever made the top 0 is where you had an x-intercept. It was where the, so there's my x-intercept at negative 2. When you plug in negative 2, you get out 0. So when the numerator of your fraction is 0, the whole fraction is 0. I mean, you get a y value of 0 there. So you kind of memorize with rational functions in college algebra. If the numerator is 0, it creates an x-intercept on the graph. Then there's the whole thing about the denominator. Wherever the denominator is 0, well, you can't divide by 0 in math. But what happens is when you get close to that number, you get a vertical asymptote. So you can't plug, well, I mean, you can plug x equals 4 in this equation, but when you plug in x equals 4, you get 0 in the denominator. It's undefined. And that's why if you were to look at this graph at x equals 4, there is no y value at x equals 4. That's the vertical asymptote right there. In fact, for effect, I'll type in x equals negative 4 so that you, excuse me, why do I keep saying negative 4? Positive 4, obviously. If you plug in positive 4 into x, it makes the denominator 0. So if you plug in 4, you don't get a y value because you can't divide by 0 in math. But when you get close to it, like if I plugged in 4.0001, the closer x is to 4, the smaller your denominator. And if you have a really small denominator, that means your fraction is going to get big because you're dividing by a really small number. So small denominator equals big fraction. So that's why the y values of the graph are getting very, very big at x equals 4. Well, excuse me, when x is a little bit bigger than 4. But I can't go back and do college algebra over again. Just realize that when the numerator is 0, you get x-intercepts. When the denominator is 0, you get vertical asymptotes. That's exactly what's going on with the tangent function. You have intercepts, x-intercepts. You also have vertical asymptotes. And why would that occur? Well, if you realize that your numerator is the sine function and your denominator is cosine, what that means is whenever sine is 0, that would mean your numerator is 0. That's going to create x-intercepts. So look at where sine is 0, either on this graph or on the unit circle. You get the sine value, or the y value, the point on the circle, being 0 if your angle is 0. You get another y value 0 here. Sine is 0 if your angle is pi. So you could look at the unit circle and say it's going to happen at 0, it's going to happen at angle pi. Or you can look at the graph and see right here, you have the y value 0 here, the y value 0 here, the y value 0 here. So sine is equal to 0 at negative pi, 0, and pi. So I should be able to look at the tangent graph, and at negative pi, 0, and pi, I should also get x-intercepts. Because if these are the x values that make sine 0, and sine is in the numerator, you're going to have 0 divided by some other number, and all day long, 0 divided by a number is just 0. So tangent is going to output 0 whenever sine outputs 0. So negative pi, 0, and pi. And there it is. At negative pi, 0, and pi, you see x-intercepts. So at least make some sense of why the graph is the way it is. The other explanation would be, well, when are you going to get your vertical asymptotes? Well, back in college algebra, you got vertical asymptotes whenever you graphed an equation that had variables in the denominator, where the denominator was 0. It didn't matter what the numerator was. I don't care what the output of sine is now. As long as the output of cosine over here is 0, I'm going to get undefined, and it's going to create potentially a vertical asymptote. So I asked myself, where does cosine function have an output of 0? Where are its x-intercepts? And that's here, 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 and here. Or if you're on the unit circle, you're looking for where the x values are 0, because x values are cosine. So that happens at an angle of pi over 2, and that's right here, pi over 2. You'll get another x value 0 right here at 3 pi over 2. That shows up right here on the graph. Right? Everything's correlated. The information on the unit circle is the same information on these trig graphs. So if you look at where cosine is 0, like negative pi over 2, pi over 2, let's just look at these two right here that I'm highlighting with the star. At negative pi over 2 and at positive pi over 2, those are the inputs, theta, that make the output of cosine 0. That's going to make your fraction, because we're graphing tangent, tangent's a fraction, sine over cosine, that's going to have your fraction, make your fraction have a denominator of 0. You're going to have vertical asymptotes, and there it is. We had a vertical asymptote at negative pi over 2 and at pi over 2. So at least have some sense of being able to correlate what's happening with sine and cosine and how is that affecting what's happening to tangent. After that, I kind of just as a student just memorized, okay, if the teacher ever makes me graph tangent, that's the one where you have a vertical asymptote to the left of the y-axis, one equidistant to the right side of the y-axis. Because I know my period is pi, I'm going to have to cut it in half. Half of it's to the left, half of it's to the right. So this would be a half a pi to the left, so negative pi over 2. Half a pi to the right would be positive pi over 2. And I just memorized it. The graph kind of looks like y equals x cubed. The difference is this has vertical asymptotes. Y equals x cubed doesn't. So I just knew. And then it's periodic, so you're just going to keep getting the same graph over and over and over. By the way, in Desmos, if you click this little wrench in the upper right-hand corner, you can change your axes. So for example, I could change this from negative pi over 2 to pi over 2, just so that I get nice clean labels. And maybe I can do a step size of half of that, which is pi over 4, just so I get clean labels. So now when I go back to my graph, you can see the vertical asymptote at negative pi over 2 is promised. Vertical asymptote at positive pi over 2. Kind of looks like y equals x cubed, but you get many, many of them. The reason I wanted to go to Desmos actually wasn't just to get a clean picture of tangent, but just to show you if you graphed cotangent, it kind of is similar. The period's still pi. The difference is that your asymptotes aren't to the left and to the right of the y-axis, that your y-axis is one of the asymptotes. You've got one here, and then the period's still pi. So if you have one asymptote at x equals 0, you have your next one at x equals pi. In fact, let me type in x equals 0 and type in x equals pi, just to illustrate that green line and that black line are the equations of the asymptotes. So you can see it right there. So from 0 to pi is pi units. The period for cotangent is pi units. It just keeps repeating itself. So let me actually, before I introduce graphing cosecant, I told everyone I wouldn't be doing that because I didn't think I had enough time, but I think I can spend 5 or 10 minutes doing a decent job on that. Once you teach a student how to graph cosecant, graphing secant is much the same. I do want to go back to the homework on 2.7 and pick out one or two problems that would remind us where we left off. So the formula for the period isn't 2 pi over b like it is the other 4 of the 6 trig equations. It's pi over b. So for example, by me not writing a b value here, right? Normally this could be written as a tangent b x minus d plus c. This is the model that we've been using all semester long. So by me not writing a coefficient on the x, that means b is 1, right? Your b value would be 1. And if you replace b with 1 in this formula, you'd get pi over 1, which is just pi, and that's perfect because it takes pi units for it to repeat itself. So just try not to get tricked because it's not meant to be tricky. It's just those are the facts, you know, and you have to know. So just to remind you, the formula is 2 pi over b for the other 4 trig functions, for sine, cosine, cosecant, and secant. So for these 4 equations, this is the formula for the period. By the way, the other things that we talked about, like amplitude is a word that only gets applied to sine and cosine. Makes no sense to talk about the amplitude of tangent or cotangent or secant or cosecant. So this a value can be thought of as a vertical stretch or compression no matter what function you're talking about. But we only refer to the amplitude of sine and cosine, and amplitude is always going to only be positive. So anyway, just wanted to remind people where we left off. So this will make sense when I go to the homework here. And so here we are, I think in 2.7. I never really got to the questions that I wanted to get to. So here's the one I wanted to get to. This is the most commonly missed question. If I was to put this on an exam, I might catch half the class, which is unfortunate because it's not meant to be tricky. This is just the way it is. So the most common mistake for the period here, after doing so many problems with sines and cosine, is to think that the period's 2 pi over b. So students write 2 pi and then b happens to be 3 here, right? B is the coefficient at x. So if you write 2 pi over 3, you're going to get it wrong, but it's also very easy to get right. Just remember the formula for the tangent is pi over b, so they're looking for pi over 3, or 1/3 pi. Horizontal shift, we talked about that yesterday, but it's a good review. Remember that the model that we've been using all semester long is not the model that all textbooks use. This idea that b is factored out is just one way of doing it. Like I said, if you randomly picked a textbook off my shelf in my office, you know, you have a 50-50 chance of the textbook using this model, and some textbooks don't factor out the b. So just realize that if you have a formula where the b is not factored out, you're going to have to do that to make everything else consistent. So for example, back to the homework question, this one, the 3 is not factored out in there. So let me move this over. So you have to do that. So for this question, I would factor out that 3. And then if you did that, I think this is where we left off last class where we did one example. If you factored out the 3 in 3x minus 6, you know, you'd have to ask yourself, what do you multiply 3 by to get -6? And that would be -2. So now, having it written this way, you can see if someone were to distribute the 3, they'd get back to this 3x minus 6. So I haven't changed the equation. This is just, I changed the way the equation looks, but it's the same equation, so it'll have the same period and the same horizontal shift. So the period, again, would be pi over b. B is 3, so the period's pi over 3. It's the horizontal shift that I want to talk about. So the next one that we get to that's the most common mistake if it's on the midterm, and both of these are likely on the midterm, to be honest with you, at least one of them, if not both. So it has to be factored out that the d in our model is only discernible when you factor it out. So common mistake is to think that this shifts to the right 6. They got the fact that it moves to the right correctly. It moves to the right by the fact that it's subtraction instead of addition. It's just that it's not 6 units, it's 2. In fact, I can just click on the little key here and it shows me the answer is 2. Try not to be tricked by that. I won't spend any more time on it because it's the same thing over and over. The issue is that because it's so easy, we don't spend much time on it. And because we don't spend much time on it, students forget this. And even though I've just said this, it won't matter. You may forget it during the test. You're so used to using 2 pi over b. You're so used to the problems and more having it factored out that when you rock the boat even a little bit, you know, we don't get good results. I think that's probably it. The rest, I think, is well, we need to spend some time graphing, but the rest is the same thing. Real quickly, this is the secant function. We haven't looked at secant function yet. We'll graph cosecant and secant in a minute maybe. But remember that for the secant, the formula is 2 pi over b. So the fact that b is 3 again, the number in front of the x is 3. The fact that this is a secant function, the formula is different than tangent, cotangent. It's 2 pi over b. So you'll notice the correct answer is 2 pi over 3 here. And then again, the horizontal shift is not 12. You'd have to factor that 3 out. If you factor the 3 out, this would become a 4. And you can see that means that things are getting shifted to the left 4. Why left? Because this is addition. So just have that in mind. What we haven't done yet is really graph secant, cosecant. And I think only because I have the time that makes sense. So I want to do it sort of methodically. I realize this isn't going to have a huge bearing on your success or lack of success in this class, but I have 5 or 10 minutes to do this. So if you go back to cosecant, the definition of cosecant is 1 divided by sine. So a common way to graph cosecant is to first to graph the values of sine and then just flip them, right? Because cosecant is the reciprocal function. So let me show you a few key numbers here. So suppose I just arbitrarily say what happens at x equals 0. Well, if your angle is 0 degrees, you could use the unit circle to say, well, if you're 0 degrees, the sine is the y value. So the sine is 0. So this right here on the unit circle tells me that if you plug 0 into sine, you get 0 out. Another way to get that same information is just look at the graph of sine. Right here is the point 0, comma 0, meaning if your angle is 0, right, my input is an angle, and my output is a ratio. In fact, that ratio is sort of opposite of hypotenuse. So if your angle is 0 radians or 0 degrees, the ratio opposite of hypotenuse would be 0. So I can use that to help me figure out what cosecant is. So cosecant of 0 would be 1 over sine of 0, but we just found out just right here that the sine of 0 is 0. So this is a good one to start with because division by 0 in math is undefined. But much like the last class period, we said there's a little bit more going on here. Those are potentials for vertical asymptotes. And it's exactly what happens with cosecant. So in blue, I'm going to graph cosecant function. Wherever your y value on sine is 0, wherever it outputs 0 here, then your denominator of cosecant here is going to be 0. And you're going to get a vertical asymptote. So if you have to graph cosecant, the first thing you do is graph sine. And then whenever you have an x-intercept, there's 3 of them on this graph, here's one full cycle of the sine. Whenever you have an x-intercept, that means your y value is 0, and that means sine is outputting 0, and that means your denominator of this fraction over here is going to be 0, making cosecant undefined. But it creates a vertical asymptote, meaning that the cosecant is either going to approach infinity or negative infinity near those lines. Same thing is going to happen at pi. At x equals pi, sine is 0. It's right there, right? That's the point pi comma 0. So the fact that's an x-intercept means if you plug pi into the sine function, you get out 0. Well, if sine outputs 0, that means cosecant is 1 divided by 0. Again, undefined, and it creates a vertical asymptote. So very easy. Graph the sine function. Any x-intercept now becomes a vertical asymptote in the cosecant. And then I continue this process now where I just pick an x value, plug it into sine, look at its output, and then just flip it to get cosecant. So that I have more room here, let me erase what I just wrote here. Give myself more room to write. So another key place would be is if I plugged in pi. What is happening with sine function at x equals, not pi, pi over 2, 90 degrees? Well, if you look at the unit circle, pi over 2 is 90 degrees. That's this point right here. And if you remember, sine is the y value, so it's 1. So that tells me on the unit circle right here that the sine of pi over 2 is 1. Again, that same information is right here in the graph. If your angle is pi over 2, just go up to the curve and you can see that the y value is 1 right there, right? That's the highest the sine function gets because the amplitude is 1 right now. So if the output of the sine is 1, then the cosecant is going to be 1 divided by that answer, right? 1 divided by sine is now going to be 1 divided by 1. So in short, if you take the number 1 and you flip it, you get 1, right? Flip 1 over 1 and you get 1. It's the one number that when you flip, it's one fraction that you flip and you get itself. So the idea is this is the one place where cosecant intersects with sine. So, and that's going to happen, the same thing is going to happen at 3 pi over 2. At 3 pi over 2, the output of sine is negative 1, right? That's the lowest sine goes. And if the sine value is negative 1, that means cosecant is going to be 1 divided by negative 1, which of course is negative 1. So the output of the sine is the same as the output of cosecant. So at your high and low points, you actually get an intersection between the sine curve and cosecant. So there's a little more to the story. See if I can, again, I know if you're taking notes, you've got an infinite piece of white paper, but I'm gonna clean this up a little bit so that I have room to write. I'll do maybe one or two more. Suppose that I look at, say, 30 degrees, or that would be what, pi over 6. If you looked at the unit circle here at pi over 6 or 30 degrees, you'd see that the sine value is a half. Remember that the sine is the y value of the point on the unit circle. So sine of 30 degrees or sine of pi over 6 radians is a half. You could get that same information if you just looked at the graph. Well, not really. It's kind of hard to tell. But the idea is we don't really care what the x value is. We could put a big question mark here. The idea is for that x value, that clearly there's an x value here that makes the y value a half. Whatever that x value is really is irrelevant. Whatever that is, question mark, the fact that the sine function spits out a half, means that cosecant would be 1 divided by that answer, right? 1 divided by sine would be 1 divided by a half. And in math, you simplify that by changing this division guy right here to multiplication, and then flip that fraction to 2 over 1. So when you have 1 over a fraction, basically it flips the fraction, which we already know this, right? Cosecant is the reciprocal of sine. So if you flip a half, you get 2. So that gives me one quick point on the cosecant function. For that mystery x value, I actually know it's pi over 6, 30 degrees. But even if I didn't know that x value, the idea is whatever this x value is that makes the y value of this curve a half, the y value of the reciprocal function would be 2. Why? Because when you flip a half, you get 2. So you start to see this. So the idea is I could continue that story. I could say, let's pick an x value, doesn't matter what it is, so that the sine outputs 1/4. Certainly somewhere in here, right, this point right here, you have a y value of a fourth. So whatever that x value is, right here, question mark, whatever that x value is right there that makes sine 1/4, cosecant would be 4 over 1. So that gives me another point on cosecant. If the y value on sine is a fourth for that same x value, then cosecant will have a y value of 4. So basically the graph skyrockets. That's why there's a vertical asymptote there. We could play this game all day long. You could pick a point where the sine function spits out 1 over 1,000, and cosecant would be the reciprocal of that, which would be 1,000. So the smaller the sine function value gets, the larger cosecant value gets. And I can make the same argument over here. Here's a point that has a really small y value, might be 1/10. So when you flip 1/10, you're going to get like 10. So the idea is you basically get this. And then to make a long story short, over here, same thing happens. If you looked at a y value of negative a half, then if you flip negative half, you get -2, which is down here somewhere. So the idea is you get the same, sort of like the same picture we just drew a few seconds ago, but upside down. So if I show you that, you do the same thing. I'm not going to do it, but if you asked me to graph secant, I would do the same thing. It's just I would have this column right here being cosine. I would take the y values cosine and I'd flip them to graph secant. It'd look a lot like what we're doing here. So to do kind of a quick summary, because it just looks good, if you let me go to Desmos.com, just because I do believe we have the time to do this, if I go to Desmos Graphing Calculator and show you, like, here's the sine function in red, and by the way, if you want to play around with Desmos, if you click the little wrench up there, you can do things like tell the computer that you want to graph the sine function from like -2 pi, and then I'll make the right bound here 2 pi, and then maybe a step size of, I don't know, half of a pi. That just gives me nice clean labels on the x-axis. And then whatever you want for the y-axis, maybe you want it to go from -4 to 4, and maybe make the tick marks 1 unit each. So the step size here is how often you want to label tick marks. And then this is like the window of your calculator, your x min and x max, y min, y max. So we get a couple cycles now of the sine function. So with that, I can also graph 1 over sine, which is cosecant, and it looks a lot like what I just showed. What we did is we graphed 1 cycle of sine. Any x-intercept in sine became a vertical asymptote on cosecant. And then the rest, basically, if there's a high point on the sine, there would be a low point on cosecant, etc. So, and it just looks like that. So if you wanted me in a very quick way, if you wanted to graph secant, then what you would do is you'd first graph cosine, and it's the same story. You'd graph cosine, you'd turn any x-intercept into a vertical asymptote, and then any high point would become a low point on cosecant. Let me just graph it and show you. Secant. Remember, secant is the reciprocal function of cosine. So it's the same story. It's just that, Cosine is basically a horizontal shift of sine. Sine and cosine are the same function, except for a horizontal shift. So you take the sine function, you move it left to right, the right amount, and you got yourself a cosine function. So anyway, this is the graph of secant, if you want. And this can get more complicated, but I want to shut up now. So for example, if you want me to graph something more complicated, like 3 secant 2 parentheses x minus 5 or some crazy thing like that, the very first thing I would do is, if I was doing this by hand, is I would graph 3 cosine 2 parentheses x minus 5. And then I would use that as a guide using the same rules. Any x-intercepts will become vertical asymptotes, any high point becomes a low point, and any low point will become a high point on secant. So when I compare the two, you see that the black graph can be easily graphed if you first graph the purple. So if I wanted you to graph something complicated like this, 3 secant 2 quantity x minus 5, you would just change secant to cosine to get that reference curve in purple in my example, and then just use that to turn it into the graph of secant. So I just want you to see how that's developed. It doesn't make sense for you to pass it through class and have no idea where the secant function graph comes from. But honestly, when it comes to the exams, like the midterm and the final, don't expect questions like that. Expect questions where I do something like this, and I ask you for the period, and then you have to say, oh God, it's tangent. Make sure you use the formula that's pi over b instead of 2 pi over b, things like that. Or things like, I don't factor the value of b out, and I ask for the horizontal shift. You know, you're going to remember to factor that 5 out. Those are the kind of things that you're going to see on the midterm. So we're talking 2 questions at the most, probably on the midterm, about tangent and cotangent, secant, cosecant. Not a lot. So I'm gonna shut up.